In this video, I'm going to describe my provably correct polygon algorithms. Here, a polygon is defined by a sequence of point locations defining the boundaries, not a set of pixels in a raster image. For background, read about the Scalable Vector Graphics Standard of the World Wide Web Consortium. Examples of these polygons range from property boundaries to parts of CAD specifications, and so on. The goal is to compute exact solutions for a polygon and a point, or for comparing two polygons. For a polygon and a point, we want to compute if the point is inside the polygon, outside the polygon, or on the boundary. For two polygons, we want to compute A and B, which is also called A union B, A plus B, which is often called A or B, A minus B, and of course B minus A. What's unusual here is that the foundations of the algorithms are provably correct. That is, no matter the inputs, they can never fail and always yield correct results. The basic algorithms are for comparing two line segments and for comparing the angles formed by rays emanating from a point. Let's consider the polygon and point first. A well-known solution is to add a line from the point to a distant location and count the number of polygon crossings. Odd equals inside, even equals outside. It sounds simple enough, but there is a problem. If the line goes through or near a vertex, crossings may be missed, counted twice, or seem to cross when it doesn't. If we look at one segment of the polygon edge at a time, what's needed is to perfectly compare two line segments. A mathematical solution is to solve the simultaneous equations of the two lines and see if any intersections lie within the segments. Even if the points in question are limited to integer coordinates, solving simultaneous equations on a computer is inexact in the general case due to round-off error. And inexact solutions lead to errors in counting the crossings when the test line is extremely close to an end of a polygon edge segment. What's needed is a totally different approach. First, some definitions. A line segment A runs from P0 to P1. Line segment B runs from P2 to P3. All 4 points have integer coordinates. In the real world, this means scaling to a large enough integer space that the points have sufficient accuracy for the problem at hand. We want to find the relationship between the two line segments. They can miss, or they can cross, or they can just touch. There are several variations of touching. P0 can touch B in its interior, or P0 can touch B at P2 or at P3, and P1 can touch B in one of those three ways, or P2 can touch A, etc. Similarly, there are several variations of the collinear case. They can miss, share some of their lengths, or one segment can contain all of the other. How can the correct situation quickly be computed with infallible accuracy? First, we will make a digression into computing the area of a polygon. A well-known formula exists for this computation. The area equals half the sum of products based on the coordinates. Proofs of this formula can be found in geometry texts or via an internet search. It's important to note that if the polygon points are in counterclockwise order, the area is positive, but if they are in clockwise order, it is negative. So there is often an absolute value operator included in the formula. However, in our case, we want potentially negative values. This is because if we let one line segment and an endpoint from the other line segment define a triangle, the sign of the area tells us if the point is on the left or the right of the line, viewing from the lower numbered point towards the higher numbered point. A zero area tells us that the point is somewhere along the extended line segment. So we compute four areas, one for each triangle formed by an endpoint and the other line. We only care if it's negative, 0, or positive. We can store these as 0, 1, and 2. Now we have four numbers that can each be one of three values. We can form a 4-digit base 3 number, and it will range from 0 to 80 because 3 times 3 times 3 times 3 equals 81. Let's consider a simple case. If P2 and P3 are both to the right of A, then the two segments must miss. This is actually four cases rolled into one. P0 can be either left or right of B, and P1 can be left or right of B. So we have a solution for 4 of the 81 cases. And for P2 and P3 both to the left of A, we have 4 more solutions. We're already almost 10% done. Note that some of the 81 cases are impossible. For example, if P2 and P3 are both to the right of A, then neither P0 nor P1 can touch B. So a couple more cases can be filled in as impossible. And 2 more can be done for them being left of A. And more can be filled in for both points of A right of B and for both of B both left of B. I made 2 paper strips representing A and B with ends labeled. By fooling around with them, I eventually filled in the entire list of 81 cases. Showing the 81 results in a 9x9 matrix showed interesting symmetries and even revealed a couple of mistakes that were corrected by careful experimentation with the paper strips. So now we have a table that contains every possible relationship between 2 line segments. Since we can compute which entry to use for 2 arbitrary line segments, we can create an algorithm that is provably correct and can never fail. A small note: to avoid any possible round-off error, we compute twice the area of the triangle so as to avoid division with its possible round-off error. Let's return to the problem of computing if a point is inside a polygon. We now have the ability to avoid double counting the test line crossing the polygon at a vertex because we can choose to include a touch at the end of the edge segment and not include a touch at the start of the edge segment. And if the test line does touch the end of an edge segment, we can distinguish when the next edge segment ends on the other side of the test line, which is a cross, from it ending on the same side, a bounce, which should not count as a cross. There are complexities. If the next edge segment lies along the test line, then we must look at the next edge and so on until they diverge. So it is now possible to build an algorithm to determine if any point is inside, outside, or on the edge of any polygon based on a line segment comparison algorithm that is provably correct. This is useful by itself and will be a vital tool for computing polygon operations. Note that I don't claim my algorithm for testing a point inside a polygon is provably correct. That would take a lot more work. Moving on to polygon comparisons, let's look at the so-called winged edge algorithm. This algorithm has been around since the 1970s, but lacked the solid underpinnings to be robust. The name, which I will not defend, derives from the data structures used to relate the edges to the intersections. A simple case involves 2 squares. The first step is to compare each edge of one square with each edge of the other square and add a point to each polygon at all the intersections. Then we create a data structure for each intersection that points to the edges that meet there. Usually there are 4 segments, but there can be more, possibly many more, in ugly cases. We now want to perform operations such as A minus B. We start at 0 and traverse along the edge until we hit an intersection. Then we bear left. That is, we look at all the edges that touch the intersection and pick the one that is most counterclockwise from the edge we just traversed to get to the intersection. We will get to how we do that later. This edge causes us to switch from traversing A to traversing B until we hit another intersection. Then we bear left again and switch back to A. We continue traversing until we get to where we started. Saving up the points on this traversal gives us a new polygon, which is A minus B. Obviously, starting at the upper right of B will generate B minus A. Starting at 0 and bearing right will generate A plus B. Finally, if we start at a point of A inside B and bearing left, we will generate A and B. And we know we can perfectly compute any of A's vertices are inside B. Let's return to the problem of bearing left or right. All of the edges we are concerned with obviously have the intersection as one of their 2 points. Let's call these rays because they emanate from one point like rays from the sun. One of the rays is the one that we traversed to arrive at the intersection. Let's call that the base array. What we need to do is sort the rays according to the angle from the base array. Of course, using actual angles would embrace lots of calculations with round-off error. Using slopes has similar problems, especially with vertical lines. Fortunately, we can create another table to solve the problem. We want to sort the rays by their angles to the base ray without using angles or slopes. To do a sort, we need an angle comparison algorithm. Once again, we use our line segment comparison algorithm to establish if a ray's endpoint is to the left or right of the base array and the ray we want to compare it to. We have to expand the collinear case into 2, in the same direction or in the opposite direction. We compare the first ray's end to the base array, the second ray's end to the base array, and the 2 rays to each other. This gives us 4 times 4 times 4 equals 64 cases. The array of answers can be filled in by inspection or by creating an algorithm to fill it, which is what I did. The algorithm had an imaginary clock with 3 hands and 8 hours. I had the hands march through all the possible positions in 8 hours. For each position, I computed which case the 3 vectors made and filled in the answer in the matrix, which was easily computed for such a simple test. This filled in the same spot in the matrix several times, always with the same value. The inefficiency was unimportant because this program needs only to be run once, and then the matrix of solutions is known forever. When using this matrix to sort rays, there is a complication similar to the one in the algorithm to test a point in a polygon. If 2 rays are in the same direction, it's necessary to traverse them until they diverge and apply the sort test at that point as if that were the intersection in question. Again, only the ray comparison is shown to be provably correct. Proving the higher level algorithm correct would require a lot more work. To find the 4 possible solution polygon sets, that is, for plus, for and for the 2 minuses, test traversals must be considered for every point in each polygon. So while we are tracing turning left, each vertex visited is marked. Every unvisited vertex is tried until all vertices have been checked as possible starting points. Then the vertices are all marked as unvisited and bearing right as traversals are done. Finally, To have bearing left and right work properly, we need to note that the holes have to have their vertices in clockwise order. Here is a simple example with holes. Each square has a square hole. A and B gives the polygons that have in common, or A and B. A plus B gives the polygon that encompasses both, which is A or B. And there's A minus B, and of course B minus A. To produce correct answers, these algorithms require clean input. Fortunately, the algorithms already described can be used to create processes to ensure clean data. For example, a figure 8 drawn in the usual way is not a correctly formed polygon because as it is traversed, part of the time the inside is to the left and part of the time the inside is to the right. But the self-intersection is easily detected with the segment comparison algorithm, and the figure 8 can be divided into two clean polygons for its upper and lower parts. Finally, the solution traverses, as recorded, do not obey the rules for counterclockwise exteriors and clockwise holes. So it is also necessary to clean this up by comparing the proper order for all the polygons and the nesting of holes. This is straightforward using the tools developed. This can also be applied to check that input data is properly ordered and nested. The source code for these algorithms is available, and a technical article is also available at these references.